motion with integrals. Let's say we have a position function, s of t. We know the derivative of position will get us our velocity function. The rate of change of your position represents your velocity. And the rate of change of velocity we know is acceleration. And because acceleration is the first derivative of velocity, it must be the second derivative of position. Now when it comes to integration, we can get a velocity function from an acceleration function or a position function from a velocity function, knowing that the integral represents the antiderivative of the function we are integrating. So, looking at an integral of acceleration. Let's look at indefinite integrals and then definite integrals. We know that the antiderivative of acceleration is velocity plus some constant c. If we're integrating velocity, we know we'll get some position function plus some constant c. Now, if we tack on some lower and upper bounds, we now just have to change our perspective and understanding of what these things represent. So we know the indefinite integral to evaluate, it's just the antiderivative. So we will get a function. We will get a position function. We'll get a velocity function. But what if we have a definite integral? Well, we know to evaluate definite integrals, we're going to apply that fundamental theorem of calculus. So we have to find the antiderivative of the acceleration, which is velocity, evaluate at the upper bound minus velocity evaluated at the lower bound. For velocity, to evaluate that definite integral, antiderivative position at the upper bound minus position at the lower bound. Now, what do these things mean? How do we interpret these calculations? Well, that is a net change in velocity. So integrating acceleration over some time period from A to B will tell you the net change in velocity. Likewise, drawing parallels here, integrating velocity over some time period from A to B will represent a net change in position. So interpreting the fundamental theorem when it comes to an application for motion is important in the context of a problem or understanding what you're actually calculating. So in general, when we evaluate an integral from A to B for some function, we can now think of that antiderivative at the upper minus the antiderivative of the lower as a net change. So that's the difference between the interpretation for the definite and indefinite integral in relation to motion. Now, if integrating velocity from A to B represents a net change in position, or the net distance traveled, can we find a total distance traveled? And the answer is yes. If we want the total distance traveled from one point to another, rather than integrating velocity, which has direction, we want to just integrate our speed. And we know speed is the absolute value of velocity. So by integrating speed from one point to another, and knowing speed is just a scalar and there's no direction involved, we can calculate the total distance traveled. Now it's important to note that it's the total distance traveled from time t equals a to time t equals b. Okay, so we want to specify the interval in which we are calculating the total distance we have traveled. And then lastly, the thing you want to be aware of for motion is if we have a velocity function and we have our current position, can we calculate our position after some time period? So if we have some velocity function and we have an initial condition like at s of 1, or we'll say at s of a, or at some point, we'll say, some value c. So what this means, we have a velo function, and we have our position at time t equals a. So think of it as an initial condition, or a position, c at time t equals a. Okay, so we have that initial condition, we have a velo, we want to know what is the position at some time b. Okay, so what we're going to do is think of it as, we know where we currently are. So let's say we know we're at S of a, and then if we add to it a net change in position from when we're starting to where we want to end up in terms of the time, we will be able to determine where we currently are from a position perspective. So where you start plus your net change in position. How do we calculate net change in position? We integrate velocity. Again, why are we doing this? Because all we have is a velocity function. Okay, if we had the position function, we could just plug in b to the position function, but we don't. We have velocity function instead. We know where we start. We can integrate from where we start to where we want to end up in terms of time, and that will equal the position at some point b. So then if we wanted to carry this further, if this was an actual example, S of a we know equals c, so whatever that constant was, plus we would have to evaluate this, S of b minus S of a, to get that change in position, and then that'll get us the position at time b. Okay? And you should even see that the algebra holds here because we know S of a is equal to c, whatever that number was. These things cancel, so the left side equals the right side. So that calculation on the left side is in fact a valid solution for how to find the position at time t equals b. You can see that the algebra holds here through the calculation. So where you start plus the net change in position will equal your position at whatever the time period is. So that general concept is one that you want to understand for motion. You're trying to calculate a position at a certain time, you know where you're starting, and you have a velocity function. So you know how fast and what direction you're going to travel based on that function. How do you calculate where you're going to end up? We'll say, I'm going to start here, and I know how to calculate a net change in my position with integration. Integrate from the starting time to the ending time. So notice that b's match, and that will get you your position at b. So that's the conclusion for motion and how it's related to integrals.